will see the potential V at an exterior point O in terms of dipole moment. Okay, right. So it will be integral V prime 1 by 4 pi epsilon naught del prime dot p bar divided by r minus 1 divided by r del prime dot p bar, that means divergence. Okay, whole dv prime. Okay, that means we are integrating with respect to the volume v prime. So the point considered is x prime, y prime, g prime as shown in the figure, and r is nothing but the distance vector from that point to the point O, that is xyz, where you are interested to find out potential V. Okay, so if you write this V in separately like these two terms, that is integral s prime p bar dot an prime bar ds bar, like this is by applying divergence theorem. Okay, divided by 4 pi epsilon naught r and plus of minus del prime dot p bar divided by 4 pi epsilon naught or dv prime. Okay, that 1 divided by 4 pi epsilon naught I am attaching with the both terms, and I apply divergence theorem for the first term. So you are getting these two terms as a sum for giving the potential. So here what is this an prime? An cap is outward unit normal to surface ds prime of the dielectric. Okay, and the first term is the potential due to surface charge distribution. Okay, that is rho s equals to p bar dot an bar, and the second term is due to volume charge distribution, that is rho v equals to minus divergence of p bar. Okay, that means in case of surface charge distribution, from that formula you can get this rho s, and from the second term you can get rho v equals to minus divergence of p bar. So these two are having some two important terms. Okay, and you all know here p bar is polarization. Remember, that is not dipole moment. I am saying it as polarization. Okay, right. So here that rho s is bound surface charge density. It is not just surface charge density. This is bound or polarization surface charge density, because it is involved with polarization concepts. And the rho v is nothing but volume charge density, that is bound volume charge density. Okay, so these rho s comma rho v are not free to move within dielectric material, but they caused because of displacement occurs during polarization. Are you getting? So these are not free to move within dielectric material, but because of the polarization concept, that is due to electrical field E bar application, they are coming in a dielectric material. Okay, consider that if the entire dielectric were electrically neutral prior to application of the electric field, that means there is no charge present prior to the application of E bar, and if you have not added any free charge, okay, this is important. Okay, then total charge of dielectric medium remains 0. Right, then if we make that equals to 0, the total charge which is found out to be closed surface integral rho s ds plus volume integral rho v dv. I think that is rho pv, that means polarization, indicating polarization p, not rho or rho, that is rho ps and rho pv, I guess. Okay, so then the bound charge qb minus qb equals to 0. That's how we are getting it. Okay, then in the second case, if you consider a dielectric region which is containing some free charge, and then rho v is volume density of free charge. Okay, then the total volume charge density, I'm saying total volume charge density is going to become rho v plus rho pv, that is due to polarization and the actually existing due to free charge, is nothing but equals to divergence of E naught E bar. Okay, like these things you can get from Maxwell's equations, right? Rho v equals to divergence of d bar, and d bar is nothing but E naught E bar. That's how I am getting this, right? So here if you write rho v equals to divergence of E naught E bar minus rho pv, so I am taking that rho pv to the other side or the right hand side. So with this you will get rho v equals to divergence of E naught E bar plus P bar. Okay, that divergence of whole thing, because rho PV is nothing but minus divergence of P bar. If you see that previous formula of potential, you can get that. So I'm combining both of them, and if you do rho v equals to divergence of d bar, right, then you will get that d bar will be equals to E naught E bar plus P bar. That is polarization, not dipole moment. And one more time I'm saying. So finally you are getting this d bar, which is nothing but electric flux density. uh, right, is nothing but E naught E bar plus P bar. Okay, right, when there is no polarization you can directly write d bar equals to E naught E bar, but I'm saying when polarization is there and it contains some free charge rho v, then you will get this thing for d bar. That is important, right? Thank you.